Okay, let's talk about utility theory. So far we've been making our decisions mostly on Bayes' decision rule. And the gist of Bayes' decision rule is that we want to make choices or decisions that maximize the expected value. And that so every time we have to make a decision between one of two options, we're looking at the expected value of each of those two options, and choosing the one that has the better expected value. And in the examples that we've worked so far, it's not just the, it's a specific type of value. Usually we've been focusing on the monetary value. Okay. And one critique of Bayes' decision rule and using the expected value is that that's the long run average. Okay. And so if you were to take a similar risk many times, you'd expect to, on average, get your expected monetary value out and sort of break even in that sense of achieving that expected value. But if you only have the decision to make once, you're going to get one of the two outcomes that are not the expected value. Okay. So you're not going to get kind of the long run average, but you're going to get maybe an extremely good outcome or maybe an extremely bad outcome. And utility theory is really built on this idea that sometimes we would prefer the a guaranteed medium outcome over the something with a better expected value, right? And maybe to kind of illustrate this, let's think of a game. And in this game, I'll offer you $500 guaranteed, or I'll offer you a 50-50 coin flip of $1,000. And if you lose the coin flip, $0. Which would you choose? I think I'm in alignment with most people that I would choose a $500 guaranteed, right? Because I can think of stuff that I can do with $500, even though both of these options have the same expected value, right? 50, if I take 0.5 times 1,000 plus 0.5 times 0, I get an expected value of this option of $500 as well. So they have the same expected value, but I would much prefer $500 guaranteed, because I can think of plenty of things to do with $500. And the chance at $1,000, even though it gets sort of the same expected value, um, there's maybe less what I'd say utility, kind of working this word in there, utility to getting that extra $1,000 that it's not worth the risk to me. Okay, let's do a variation on this question. Ask yourself, how much would you pay for a 50-50 ticket, lottery ticket or something like that, of $0 or $1,000? How much would you be willing to pay? If you said you'd take $500 guaranteed, then you'd probably not be willing to pay $500. But would you pay uh $300, $400, $200, only $100? What's the most you'd be willing to pay for a 50-50 chance at 0 or $1,000? Okay. Keep that in your head, and we'll come back to that, and I'll kind of provide maybe my answers of what I've kind of thought through a little bit as I'm recording this video. But keep that in mind, and let's introduce this idea of utility. So utility provides an alternate scale And the goal of this scale is to account for essentially our willingness to risk or be risk averse. Okay. Essentially accounts for maybe the reduction in value that we might have whenever we're faced with uncertainty or something like that. Or also sort of the diminishing value of money as it gets larger, right? We might place more value on the first $100 that we get guaranteed versus the chance of something larger. Okay. Uh, yeah, so it accounts for changing value of money. So not all money has the same value to us, right? So even though this has an expected value that's the same as that, we would probably prefer the $500 guaranteed than the 0 or 1,000. Okay. And that's probably because we don't value $1,000 as twice as valuable as $500. Okay, that's another way to put it. Okay, so let's sort of define this utility, and so this is going to be a function, and so we're going to define sort of U of A is going to be the utility of outcome A or choice A. Okay. Um, let's kind of put down some properties that will sort of guide our building of this utility function that takes an outcome and gives a value on some scale. Um, for any two outcomes, A and B, just kind of giving names to, this could be two choices that we're trying to choose between. Do I want to do this or do that? These could be our decision alternatives. Um, we would say that the utility of A is bigger than the utility of B if A is preferred to B. So if something is preferred to something else, it's going to have a higher utility. Okay. And if the utility of two outcomes is equal, we'd say we're indifferent. We would just as much have either outcome if they have the same utility. Okay, and so if you come to a fork in the road and both options have the same utility, then you don't care which one is chosen. Okay, if you do care which one is chosen, then whichever one you would prefer has the higher utility. Okay. Uh, and then the other thing that we have is we need to have a way to deal with uncertainty. Okay. And so if we have a guaranteed outcome, so if we have a guaranteed outcome, C is indifferent, so it has the same utility as a lottery, or just this lottery could just be some uncertainty in a fork in the road, right? Some chance event in your decision analysis. Um, and a lottery that gives outcome A with probability P and outcome B with probability 1 minus P. Okay, so those are the two outcomes. So if you have a lottery with two outcomes, and the probability of outcome A is P, and the probability of outcome B is 1 minus P. And if that lottery is equivalent to something that's guaranteed, then the utility of C, so the utility of our guaranteed outcome, is equivalent to P times the utility of A plus 1 minus P times the utility of B. Okay, what this says is essentially the utility of a lottery or utility of some uncertain outcome is the expected value or the expected utility. Okay, notice this right-hand side is how we compute an expected value, where we take a probability times a value. Now, the values that we're talking about are utilities. And so if we got uncertain outcome A with probability P, this is sort of the utility that we expect to get from A, and this is the utility that we expect to get from B. And so the utility of our guaranteed outcome, that's going to be 100% C, is equal to this. Okay, or the expected utility of the lottery, right? And we said, yeah, and so we can essentially define that as the utility of our lottery. And we said that C is indifferent to our lottery, and so maybe I wrote this kind of these equalities in the same wrong order, but the yeah, U is indifferent, so these two are equal. And if this is how we define the utility of a lottery as the expected value or the expected utility of that lottery, then that's how we can define utilities for anything that's uncertain. Okay, let's do some examples where we'll kind of see this in action. Let's return to my offer of how much would you pay for a 50-50 ticket that's either 0 or 1,000? So okay, now let's fix a couple utilities. I'm going to say U of $0 is 0. Okay, you have a couple choices, and I'll kind of make this a little bit clearer later on. You can always choose to fix two utilities. Okay, mostly because if we kind of are looking at this formula down here on how we compute the utility of a lottery, if we add everything to all those utilities, they sort of all shift up by something. If we multiply all the utilities by something, they all sort of shift or get scaled by the same thing. So we sort of can fix two of our utility values as landmarks and base everything relative to those. Okay, so I'm going to fix the utility of $0 is 0 and the utility of 1,000 is 1. Now let's talk about what would be the utility of a 50-50 lottery of 0 or $1,000. Okay, well, the formula that I just gave you gave us a way to compute the utility of a lottery. It's going to be the probability 0.5 times the utility of $0 plus the probability of the other outcome, which is also 0.5, times the utility of $1,000. And so since I chose the utility of $0 to be 0, that term goes to 0. And because the utility of $1,000 is 1, this gives me a utility of 0.5. Okay. And so what did you answer? How much would you be willing to pay, or what would be a equivalent offer for me to make to you guaranteed that would make you choose the 50-50 lottery or be indifferent to the 50-50 lottery or the guaranteed amount? Okay. I said I would pay $100 for that lottery. Okay. I'm not willing to risk much. Kind of like, yeah, I'd rather keep, I'd be just as well, like I can risk $100 and that wouldn't hurt my pride too much or wouldn't affect my finances for the month too much. And that's about as much as I'd be willing to risk in order to get a 50-50 chance at 1,000. Okay. And so my utility and utility is going to be different for each individual or group of individuals that are a decision-making unit. So that tells me that my utility for $100 is going to be equivalent to the utility for this lottery is going to be 0.5. Okay. What about let's do another kind of lottery, and now let's kind of move the goalpost a little bit. Uh, let's look at another lottery. We'll keep it a 50-50 lottery of 100 or $1,000. Uh, let's think about this. So I just established that my utility of $100 is 0.5. So I'll get 0.5 times the utility of $100 plus 0.5 times the utility of $1,000. I said the utility of $100 is 0.5, and so this is going to be 0.5 times 0.5, which is going to give us 0.25 plus 0.5 times the utility of $1,000 is 1, and so this is going to be 0.5, and so that's going to be 0.75. Okay. How much would you be willing to pay for a 50-50 lottery that gave you either $100 or $1,000? I'd pay at least $100, right? Because you're guaranteed to get $100. Um, and thinking about it, maybe, uh, I would pay $200 for that lottery, right? It's sort of maybe you've picked up a pattern. I'm at most willing to risk $100 loss is the most that I'd really be willing to risk. Okay, and so that tells me that my utility of $200 on this utility scale is 0.75. Okay. And then I could kind of repeat this with other lotteries, comparing other amounts. And I don't have to always make them 50-50 lotteries. But I could kind of fill in other lotteries with other amounts. And then let's kind of look at a plot of utility versus kind of dollar amount, or what I'll call MV, monetary value. Okay. So I've set it up so that, 0 and 0, that $0 is equivalent to 0 utility. And over here, $1,000 is equivalent to 1 on the utility scale. Okay. And then at $100, which is pretty close to 0, that gives me a utility of a half. And at $200, I said that gives me a utility of 0.75. And so if I were to kind of connect these dots to kind of interpolate my utility function, you'd get something that looks like this. And maybe we'd compare that to a linear utility function that kind of goes a straight line from 0 utility to 1 utility, going from 0 to $1,000. This line is called the EMV line. This is what you do if you always chose the expected value and said, I'll take any lottery at its expected monetary value. Okay, and that's what EMV stands for, expected monetary value. Okay. here you'll notice my utility function goes above the EMV line. And so I'm relatively risk averse. Okay, and anytime you have a utility curve that is sort of concave down, then that individual, at least for that region of decision making or monetary value, is risk averse. On the other hand, um, you could imagine a scenario where I'm being offered these lotteries and I may be short on my monthly mortgage bill, and there's a certain amount that place a high utility on getting at least this much out, right? And so if you think about it, let's say I needed to get $800 to break even for the month and be able to pay my mortgage or something like that. Um, I might place, I might not be willing to offer accept any guaranteed offers that were less than $800. And so I might place zero utility on anything less than $800. And then I would put sort of uh, equivalent utility to $1,000 on anything over $800. And so you might get something that looks like this. And so depending on the scenario that you're in, or kind of the scenario that your business or company is in, you might have different sorts of utility curves that equate your monetary value to how much you value that. And so this is sort of maybe what I need. Right? And anytime you have a concave up or a concave up utility curve, then that would be for people who are more risk seeking. And so if you're desperate, right, you gotta make the bills, otherwise you're gonna be down and out anyways. Then you might be willing to take on more risks and have something that's more concave up. So you'll see this in startups where as a startup, you're not gonna make it if you just take the safe bets all the time. You gotta take what might be some risky bets. And the nice thing if you're a startup, if those bets fail, you go bankrupt and you start again. Sort of and that's the sort of mindset of if you're in sort of a startup type mode. On the other hand, if you're a established company, you might not want to take any bets that jeopardize what you've built as a company. Okay. And so then you're more likely to be on this risk averse side. Okay. So that's the big idea behind utility curves. And this kind of illustrates how you build them. Let's kind of formalize how we can build utility curves or utility functions for making decisions. So this is what's called the equivalent lottery method. It's very similar to what I just did, but a little bit more formalized. Okay, step one. So for you, let's say you got a decision analysis problem. Okay, it's got various payoffs in your payoff matrix um, that you're interested in. And first thing you do is you fix the largest and smallest payoff. Okay, so for largest payoff, we'll call that largest payoff P max. We'll set our utility of that largest payoff to be equal to 1. Okay. We have some freedom when we're forming these utility functions. Their values are sort of relative to each other. And so on an absolute scale, we can kind of fix two of the values. And, and so we usually fix the largest and smallest payoff at 0 and 1. So the utility of P min is 0. This is done for ease of use, but I will say that if the different payoff makes more sense to fix at 0 or 1, go ahead and do so. And then you can get utility values that are outside of 0 and 1. The nice thing about this, if you set your largest at 1 and smallest at 0, then everything becomes your utility becomes a scale between 0 and 1. Okay. Okay, now we need to find our utilities of every other payoff that's in our decision analysis. And so to determine U of M for any other payoff, okay, so let's say we've got some other payoff. It's not our largest, it's our smallest, but some in between. We offer the following. So you offer the following to whoever the decision maker is. If you are the decision maker, you consider the following offer yourself. Okay. The two things that you're trying to decide between is a lottery that pays P max with probability and P min with probability 1 minus P. Okay, so it's a lottery that either has a prize of P max that has a probability of P of that largest payoff, and P min with probability 1 minus P. Okay, I will sort of on the side here note that the utility of this lottery is going to be P times the utility of P max, which is 1, times 1 minus P times the utility of P min, and the utility of P min is 0. So the utility of this lottery is P. Okay. Or a guaranteed payoff of M. M being the value that we're trying to determine the utility function for. Okay. So you consider these two options, and then you ask, what value of P makes the options indifferent or equivalent? Okay, and so what value would you have to put on the probability of getting the largest payoff versus the smallest payoff would make it equivalent to a guaranteed payoff of this intermediate payoff? Okay, so they have to decide what value of P makes these two options equivalent or indifferent. And because if they're indifferent, then their utilities are the same. That tells us then that the utility of our intermediate payoff is whatever value P we chose that makes these two equivalent. Okay. So, and then after that, once we've used this and we repeat this with any other intermediate payoffs M, then we've sort of determined the utility of all the relevant payoffs for our decision analysis. And then the key idea is that instead of using Bayes' decision rule with expected monetary values, we use Bayes' decision rule with expected utility values. Okay, and we do the whole process of making decisions that maximize the expected utility instead of the expected monetary value. So essentially, we're able to swap out any monetary values for utility values. Okay. For your homework, the one question that asks you to determine utilities has you working with Who Wants to Be a Millionaire? And in that case, we've got payoffs of 32,000, 250,000, 500,000, and 1 million. And so in part B, where it asks you to determine the utility or make a utility function, what you're going to do is you're going to fix the smallest one at 0, the largest payoff at M. So your utility of $1 million is 1. The utility of 32,000 is 0. And now what you need to do is ask what value of P would make a guaranteed 250,000 equivalent to a lottery where you had a P probability of getting $1 million and a 1 minus P probability of getting $0. Okay. And then you repeat the same for 500,000. What probability P makes a guaranteed 500,000 equivalent to a P probability of getting 1 million and a 1 minus P probability of getting 32,000. Okay. So you fill those in using this equivalent lottery method. And I'll be interested to see what people come up with the utilities for 250,000 and 500,000. If you were going pure expected monetary value, you'd expect this one to be somewhere around 1/4 and this one to be somewhere around 1/2, actually just a little bit more because the minimum payoff is not 0, but 32,000, but pretty close. But I'm expecting that most of us will value guaranteed 250,000 more than just a 25% chance of getting $1 million. Okay. So fill in what you would put there. And then repeat the decision analysis, but instead of having the monetary values at each of the sort of payoffs that you're using, use the utility values of 0 and then whatever you put in here and then 1 as those payoffs. Okay. So that's it for this video on utility theory and the equivalent lottery method of building utility functions.